Two other pieces of information here. Let's say we know f. Okay, so let's suppose, for example, that f of x is a function that looks like 3x squared plus 1. We could find f prime. We could walk through the same steps that we did earlier and use that limit definition to find a new function over here. Okay, but because that function is a function, we could actually also repeat the process and do it over again, and we could find the derivative of the derivative. Okay, so there's no reason why we can't talk about the way that the derivative is changing, or the slope of the tangent line of the derivative function. Okay, and here's what that notation would look like. This is, we would call this a second derivative, or a derivative of a derivative. And it would look like f double prime, or with like two little apostrophes there, f double prime of x. And guess what? That in itself is a new function. So if we really wanted to, if we had good reason to, we could go and we could find a third derivative, three little primes there, of x, and it would be the derivative of the derivative of the derivative of the original. Sometimes doing this is helpful. Sometimes you kind of get to the point where you're like, why am I taking so many derivatives? Does this have significant meaning? But it depends on the context that we're in. And that does tell us about something about the problem. In fact, you may remember that talking about a first derivative, two words that we used that were exactly the same as each other on the first page of this video was, we talked about words speed and velocity, okay? Saying that a derivative is also a speed, it's also a velocity. Well, for a second derivative, the word that we would use to talk about what the second derivative is telling us is this is actually what acceleration is. So acceleration is talking about a second derivative, and it's talking about the rate at which you are speeding up. It's the rate at which your speed is changing. In other words, it's a speed of a speed. And so your acceleration as a second derivative, that can be very useful in a real world context, a real world situation. There are other places where a third derivative, a fourth derivative could be really helpful. So just something to keep in mind, that when we find a derivative, we're finding a new function. There's really no reason we couldn't go find the derivative of that new function as well. Okay, one last piece, almost last piece, is that there's a little bit of new other notation that we could use. We've been using f prime of x to talk about the derivative, and really we could also use this notation, and won't get into it too much, but basically as far as the origins of calculus, there are actually two guys who kind of created calculus simultaneously, who lived in different countries, didn't have anything to do with each other, and they both came up with important ideas. So you can go look that up on your own. Go Google search Newton versus Leibniz, or who founded calculus, and you can read all about that. But they both had different notations to talk about the derivative. And the notation that we've been using, this f prime of x, is actually Isaac Newton's notation. And there's other notation that we could be using that looks like this. It says d divided by dx, d over dx, of a function y. And so d over dx of y, or I should say d, let's, instead of using y, I'll use f in both of them. So d over dx of f of x. And this says that the top d is talking about the derivative of a function, and then the bottom dx is talking about with respect to which variable. So what is actually changing? This d notation is kind of like saying delta y divided by delta x, which you may have seen before. Delta y divided by delta x is talking about the change in y value divided by the change in x value. That's kind of what's happening here. This d over dx is saying the change of what? So d over dx of f of x is also sometimes read, or you can also write it as df over dx, like this, same idea. You could put the f in the top of the fraction instead of out on the end. But this is kind of like saying, how is f changing as x changes? Or if it was dy over dx, how is y changing on top as x changes on the bottom. It's kind of the same notation as this dy dx. So I just say that because you'll see that notation as well. We'll use both of these throughout the semester, but it's good to just get comfortable with both of these as we go. Okay, let's go ahead and that's it for the examples here. Let's go ahead and take a look at one last idea with derivatives. And this actually wraps up the chapter in the book. And so the question we could have is, where does a function have a derivative? Can we just talk about any function f as having a derivative for any value of x? And that's not actually true. If you remember in an earlier example, we had to be careful about what the domain of the function was, because f can't have a value like 2 for a derivative if the value of 2 is not even in the domain to begin with. Okay, so what a reasonable question is, what does f, the original function f, need in order for f prime of x to exist? Or you could say f prime of a to exist at a specific value. So in other words, what's the criteria for a derivative to make any sense, or for us to be able to talk about this? Okay, there's actually two criteria. I guess you can break it down into two criteria, I guess. So the first criteria, as you might have guessed, because the way we've set up the course and what we've been talking about earlier, is that f needs to be continuous. Okay, let me be a little more specific here. Let me phrase it like this. I'll put it as f prime of a. So what does f need for f prime of a to exist? F needs to be continuous at a. Okay, so it is possible for f to have a derivative everywhere except for at one point, and it could be a problem that f is just not continuous there. In fact, that's what we had in the earlier example. When we had said that there's a problem at x equals 2, it wasn't just because f doesn't have a derivative there. It's because that value didn't even exist, or that function didn't even exist at 2. So f wasn't even continuous at 2. We didn't even have a chance for f to be differentiable or to have a derivative. What is interesting is it turns out that that's not the only criteria. Okay, it's not the only criteria to say if f is continuous, then it has to be differentiable. Here's an example. You've seen a graph of an absolute value function. Okay, so absolute value function looks like this. It looks like a V. There are a lot of other examples like this. This is probably the easiest one to come up with. And f prime actually exists everywhere on this graph except at x equals 0. And so this is interesting because if you think of the absolute value graph, this graph is continuous everywhere. It's continuous on the interval from negative infinity to positive infinity, no issues. Okay, but it does not have a derivative for every single value of x. It has a derivative for almost every value except for at x equals 0. So what happens at x equals 0 that makes this that makes f not be differentiable or not have a derivative at that point? Well, I've seen this phrased in a number of different ways. Here's how I'm going to say it. In order for f to have a derivative at a specific point, f needs to be, I'm going to put it in quotes here because it's kind of an informal definition or an informal term, but f needs to be smooth. Okay, in other words, no corners, or you could think about kind of sharp edges. No corner points, essentially. And this, on the absolute value graph, at x equals 0, there's kind of this sharp turn from, by the way, absolute value is actually kind of a piecewise function. So you kind of jump from one piece to the other piece, and it takes this really sharp turn. It's not like there's a smooth kind of curve to it at that point. Now, most of the functions that we're talking about are continuous, are smooth. We really wouldn't be talking about the derivative if that wasn't the case, but it is just good to kind of keep an eye out for that and have that in mind of, is it continuous, is our function smooth?